Welcome back, P-Tech and MCA students, to this comprehensive explainer. Today, we are diving deep into the absolute essentials of OOPS with Java Unit 2. I'll be your instructor, and we're going to take a really detailed, step-by-step approach to making your object-oriented Java code completely robust and highly concurrent. We're going on a journey from understanding those catastrophic system-breaking crashes all the way to building high-performance, multi-threaded applications. Okay, grab your notes and let's dive right into this.
Here is our roadmap for today's lecture. We're going to kick things off with an introduction to exception handling, then we'll compare checked versus unchecked exceptions. After that, we'll unpack the specific keywords in exception handling and explore custom exceptions and errors. Then we'll shift gears entirely to look at input and output basics, and finally, we'll wrap up the whole thing with multi-threading in Java.
All right, let's jump right into Section 1, Introduction to Exception Handling.
So, to write flawless Java applications, we first have to understand what exactly goes wrong when our code suddenly just stops. What exactly is an exception? Well, by definition, an exception is an unexpected, unwanted, or abnormal event that happens at runtime, and it completely disrupts the normal flow of your program's instructions. Think of it kind of like when you're watching a really good video online and suddenly your Wi-Fi just drops. Did you want that to happen? No. Did you expect it? Definitely not, but it completely halts your normal viewing experience. In Java, if a runtime error like this isn't handled properly, the Java Virtual Machine, the JVM, just pulls the plug. It abnormally terminates your program right then and there. That means any beautiful, brilliant lines of code you wrote after that point, they're simply never executed. Exception handling is the safety net. It's the robust mechanism we use to catch these issues gracefully, allowing our program to either recover or, at the very least, shut down safely.
Let's pop the hood for a second and look at the throwable hierarchy. This brilliantly illustrates how the JVM actually categorizes these disruptions. Basically, it's the family tree of things going wrong. Everything stems from the granddaddy root class, java.lang.throwable. From throwable, the tree splits into two completely different main branches, error and exception. Under exception, we branch out even further into runtime exception, which represents our unchecked exceptions, and then all the other checked exceptions. Understanding the specific hierarchy is absolutely critical, guys, because it dictates exactly how we, as programmers, are supposed to react to different types of failures in our code.
Now, looking at those two main branches, notice how exceptions represent application-level issues that we can safely recover from. Errors, on the other hand, represent critical, JVM-level failures that force an absolute termination. To put it simply, an exception is like hitting a pothole. An error is like the entire bridge collapsing. If you encounter an exception, like a null pointer exception or an arithmetic exception, these are totally manageable conditions. Your application can and absolutely should catch them. But an error? That's a severe, critical problem at the system level. Think of an out-of-memory error or a Stack Overflow error. A typical application simply cannot catch or recover from an error. If an error occurs, it's game over. Your program must terminate.
Moving right along to Section 2, Checked versus Unchecked Exceptions. Let's see how the Java compiler treats these differently.
Now that we know where exceptions sit in the hierarchy, we need to talk about timing. The core difference here lies strictly in the compilation process. Checked exceptions are checked at compile time. The Java compiler acts like a super strict bouncer here. It literally forces you to explicitly handle them using a try-catch block, or you have to declare them in your method signature before you can even run your program. If you refuse, your code simply will not compile, period. Classic examples include I/O exception or SQL exception. Unchecked exceptions, however, are totally different. They slip right past the compiler. They aren't checked until the program is actively executing at runtime. These usually indicate that you made a programming mistake or a logical flaw, and the compiler assumes you know what you're doing, so it doesn't force you to handle them explicitly.
So who are these unchecked villains slipping past the compiler? Well, some of the most notorious ones include the arithmetic exception. You trigger this if you try, say, dividing a number by 0. It's mathematically impossible, so the JVM panics at runtime. Another classic is the array out-of-bounds exception. Imagine you declare an array with a size of 3. That means it only has indexes 0, 1, and 2, right? If your code attempts to access index 5, which simply does not exist in memory, the JVM throws this unchecked exception immediately. And of course, there's the null pointer exception, the absolute bane of every Java developer's existence. This one usually strikes right around 2 a.m. when you're exhausted, and it happens when you try to manipulate an object reference that has a null value, like trying to find the length of a string that you never actually initialized. Okay, Section 3, Keywords in Exception Handling. How do we actually fight back against these crashes?
Well, Java provides us with a really strict toolkit. We don't just guess how to handle a crash. We use 5 fundamental keywords specifically designed for exception handling. But before we look at the exact words, let's look at the flow of a rescue operation. Step 1 is normal flow. Your code inside a try block executes happily, line by line. Then, Step 2, an exception occurs. The moment a crash triggers, the JVM entirely abandons that normal sequential flow. It immediately skips any remaining instructions in that block. Step 3, catching control. The control is transferred instantly to our catching mechanism to handle the error. And finally, Step 4, finally execution. Regardless of whether an exception occurred or was caught or whatever, the JVM always finishes with a final execution cleanup block.
Let's actually put on our JVM hats for a second and patiently trace through a real code scenario. Imagine we start the program, we enter a try block, and then we hit a risky line. Int results equals 10 divided by 0. Bam! This division by 0 immediately throws an arithmetic exception. Now here's what is absolutely fascinating about this control flow. Any line of code immediately following that division inside the try block, it's permanently skipped. The JVM just bypasses it entirely. It jumps straight down into the catch block to print an error message, and then it continues down to the finally block. It completely abandons the rest of the original try block.
Let's look a bit closer at these first 3 keywords. Think of the try block as your safety net. We suspect a specific chunk of code might fail, so we wrap it up securely in a try block. If it does fail, the catch block sitting right below it takes over. Instead of a terrifying red system error crashing the program, we can print a graceful, user-friendly message. And you know what's cool? You can even chain multiple catch blocks together to handle different, very specific exceptions. Then we have the finally block. This block is incredible because it executes absolutely no matter what happens in the try or catch blocks. Success, failure, doesn't matter. It's primarily used as a janitor to ensure critical system resources, like open file streams or database connections, are properly closed and released, regardless of any crashes.
Moving deeper into our toolkit, we have our last 2 keywords, and they sound really similar: throw and throws. Let's look at the first one, the throw keyword, spelled without an S. This is an action. It's used by you, the programmer, to explicitly create an exception object on demand using the new keyword. You are manually triggering a crash scenario, maybe because a specific business rule was violated by a user. Now, contrast that with throws, spelled with an S. This is placed way up in the method signature. It acts as a strict warning label. It tells whoever is calling this method, hey, heads up, this method might generate an exception, so you need to be prepared to handle it. It literally delegates the responsibility of handling the error up the chain to the caller.
Section 4, custom exceptions and errors. Let's see how we make this system work perfectly for our own specific apps.
So sometimes standard libraries just aren't enough. Built-in stuff like null pointer exception covers general programming flaws. But what about rules specific to the software you are building? Say, a user tries to withdraw more money than they have in their bank account. Java doesn't have an insufficient funds exception built in. So we create custom exceptions by extending the base exception class and passing a custom message up to the parent constructor using super ... It makes your code incredibly modular and super easy to diagnose. But while we're making our code robust, just remember what we said about errors earlier. An error, like out-of-memory error or Stack Overflow error, is a devastating hardware or JVM collapse. We can write custom exceptions all day long, but those system-level errors, totally unrecoverable.
All right, with our application now thoroughly crash-resistant, let's transition to Section 5, Input and Output Basics.
So we need to move data in and out of our files effectively. In Java, all the classes required for stream manipulation live in the java.io package. Just as a continuous flow of water creates a physical stream in nature, a data stream manages the continuous pipeline of data moving from a source to a destination. The first major category here is the byte stream. A byte stream provides a super convenient way for handling the input and output of 8-bit raw binary data. Because it reads raw, unformatted bytes, it is absolutely perfect for handling non-textual data. If you are dealing with audio tracks, video files, zip archives, or executable files, byte streams are exactly what you need.
Conversely, we have the character stream. Now, a character stream is explicitly engineered for 16-bit Unicode characters.
This makes it the superior and frankly the exclusive choice for reading and writing textual data. Think about it. If you are parsing international text with special characters, or reading CSV files, or scraping HTML documents, you absolutely want to use a character stream. It ensures that your text is read exactly as a human would read it, character by character, without experiencing any bizarre data loss or weird formatting corruption.
Let's do a quick side-by-side comparison, because the naming conventions here give you a huge hint. Byte streams handle that 8-bit raw binary, best for media. Their abstract superclasses are instream and outstream, with concrete implementations like file instream and file outstream. See the pattern? On the flip side, character streams process 16-bit Unicode for text documents. Their base abstract classes are reader and writer, with implementations like file reader and file writer. Oh, and one massive takeaway here. Whenever you do any of these I/O operations, you must wrap them in try-catch blocks, and you must always close your stream resources in a finally block to prevent nasty memory leaks.
And that brings us to our final segment, Section 6, Multithreading in Java. Let's really turbocharge our code.
So far, we've been looking at executing simple, sequential steps one after the other. Multithreading allows us to level up and run multiple heavy processes simultaneously. But what exactly is it? It's a core Java concept that allows a single program to execute multiple lightweight threads concurrently. And when I say concurrently, I mean at the exact same time, absolutely maximizing your CPU's utilization. Think of multithreading like a group of friends building a house together. If one friend is building the roof, while another is laying down the stairs at the exact same time, they are acting as independent threads. They dramatically cut down the total processing time because they don't have to wait on each other to finish. It leads to incredibly fast, responsive applications.
Now, Java actually gives us two distinct ways to create these threads. Let's look at the first method, inheriting directly from the thread class. It's pretty straightforward. You just create a class that extends java.lang.thread, you override its built-in run method, and you drop your concurrent logic right in there. Then you instantiate your class and simply call .start. Easy, right? Well, there's a catch. A pretty massive limitation, actually. Because Java does not support multiple class inheritance, by extending the thread class, you permanently lock your class from ever extending any other parent class in the future. You're basically painting yourself into a corner architecturally.
Because of that inheritance trap, let's look at the second method, which is pretty much the industry standard. Instead of extending a class, we implement the runnable interface. You implement runnable, you override the run method, and then, here's the trick, you pass your runnable object into the constructor of a brand new standard thread object. Why is this better? Because you only implemented an interface, your class remains entirely open to extend a different parent class later on. It's so much more flexible. And just to track its life cycle. Once created, your thread sits in the new state. The moment you call start it wakes up, transitions to runnable, and is entirely managed by the Java thread scheduler.
Wow, we have covered an immense amount of ground in this explainer, from the deepest roots of the throwable hierarchy to spinning up simultaneous execution threads. So as we wrap up today's masterclass, I want to leave you with a real architectural challenge to think about. If multi-threading drastically improves performance, but simultaneously risks insanely complex logical crashes if it's mishandled, how will you architect your next Java application? Finding that perfect balance, lightning-fast concurrent threads on one hand and bulletproof exception handling on the other, is exactly what separates a basic coder from an elite software architect. Keep experimenting with your code, always remember to catch those exceptions, and I'll see you in the next explainer.